Before I get started, I really just want to say that I am incredibly fortunate to work with an amazing team of people. And so while I get to be the one standing up in front, this is really their work. I specifically want to point out, although they're toward the back in this line, Martin and Maciej are the second and third from the back. They are actually instrumental in the work that I'm going to talk about. We were really fortunate. They're visiting scientists, students actually, who came over from the Czech Republic and spent a year with us and helped us do what we're going to talk about today. So so let's get started. We're going to talk about games and AI in games. And there's a long history of AI in games. And you don't even have to think back very far before you think of a result that's really exciting, right? We were very excited in our department in 2016, just last year. AlphaGo beat Lee Sedol. This was a long time coming, and U of A people and trainees were instrumental in that result. Maybe you want to think further back, right? It wasn't. It was about 10 years earlier than that. We had Jonathan Schaefer here at the U of A solve checkers. This is the first time that we saw a game the size of checkers that could actually be solved, so they would have a perfect strategy. It can't be beat no matter who it plays against. But probably the thing you probably most think of is in 1997, right, Deep Blue beat Kasparov in chess. This really was a turning point. Chess for a very long time was held on a pedestal that if we could get computers to play chess, we must be doing something in the direction of AI. But maybe you're really old school, right? Like this. Okay, sorry, we got to do this first. Jonathan was the first person to actually have a program that beat top players at a game and won a championship, which actually happened in checkers 3 years before Deep Blue. But if you're old school, you got to go way back, right? This started a long time ago. Turing and Shannon thought about these things as they were developing the principles of computer science. So Turing, in fact, had a computer program before there were computers. He actually wrote a program, and he played chess with somebody while he was executing his program to see how it would work, because he didn't have a machine to run it on. But it goes really before that. Before we really even began computer science, we were thinking about game theory and how we could mathematize so that we could take what looks like intelligence, how we think about playing games and making decisions, and we can mathematize that, which is what von Neumann had done in sort of his famous work that started game theory before he switched over to computers. But I can keep going back, right? It really is the beginning of any thought of actual machine processing. Charles Babbage and Ada Lovelace, when they were building their analytic engine, they were actually dreaming that it could play chess. They actually had plans in Babbage's notebooks of an automaton that would play tic-tac-toe, and he was going to tour around the UK, make a whole bunch of money, and then he was going to use that to build his analytic engine. Ada Lovelace bet on horses. I think using some mechanical process. That didn't go too well for her. But anyway, from the very beginning, it doesn't go too well, by the way, if you try to do it now either. But from the very beginning of thinking about computers, we've always sort of saw games as a part of this, just like we saw AI as a part of computers. And there's good reason for this. It's the same reason that we have our children play games. Yes, maybe it's so that they're occupied and then we can do important things. But no, we really do it because there's a whole slew of important skills, life skills, that you actually pick up through the process of games. It starts at a very early age that you learn about colors and numbers, pattern matching, and then you move on to realizing that your actions can have effects on the world. And you can plan for that now. You can do this short-term planning. If I do this, I will get my goal. And then, of course, longer-term planning, if I can strategize about reaching some longer-term problem or do some problem solving. And then, of course, the games involve multiple people playing. And so cooperation and building up social skills where you learn to become not a poor loser and a good winner. All of those things get embodied in games where we don't have the sort of consequences of real-life decisions, which need all of these things too, but we don't have the same consequences when we make mistakes. And so we can learn all of these skills in the context of games. And so games sort of serve for our children as a proving ground, a chance for them to try out their thinking processes and refine them so that they can actually use them when they move on to more important real-world tasks. Now, this is about AI, though, and AI needs a proving ground, too. And this is what games have done for AI. Because what do we need our AI systems to do? They need to do all those things, too. Right? They need to understand colors and numbers and pattern matching, and they can have effects of their actions and do short-term and long-term planning. They need to be able to do strategic thinking and problem solving and be able to work with other agents in the world and be able to cooperate with them and become good winners and not poor losers and to have developed social skills as well, too. And so we have our AI systems play games because we need them to have a proving ground before we put them off on our real world problems we care about. All right, that's my spiel for games, but if you look at that history that I just laid out of how AI has been wrapped up in games from the beginning, they're all games that look kind of like this. They're all games where there's like a board and we're manipulating the board. And so technically what we call these games is these games are perfect information games. They're games where all the information you need to make your decision is right there in front of both of the players, and we all know this. There isn't anything else that's missing. Now, from the very beginning of computing and game theory, John von Neumann, when he was developing the theory of game theory, the theory of games, didn't think these kinds of games. He wasn't actually thinking about them at all. He said real life is not like chess, is what he was talking about. Real life consists of bluffing, of little tactics of deception, of asking yourself, what is the other man going to think I mean to do? And that is what games are about in my theory. What John von Neumann was thinking about as he was moving to develop what was going to be game theory and moving to develop what was going to become the beginnings of computer science was poker. And I'm not making that up because, in his seminal book, there's a whole chapter called Poker and Bluffing. Like, that's what he was thinking about. That was the game that was driving him to how do we mathematize what's going on when we play a game like this. Now, you don't need to know almost anything about poker to understand this talk. There will be 3 brief interludes where I will pause from what I'm saying to tell you a little bit about poker, and I'm going to have John jump in to let you know when I'm doing that. So right now, let me just say that the way the game of poker works is 2 players are going to be dealt some cards, and they're going to keep them private, and the players are going to bet on whose cards are better. There might be other cards revealed, and depending on the rules of the game, there are other things that can happen. But fundamentally, you're trying to figure out who has the better cards by making a series of bets. It's tricky because you don't know what the other player's cards hold, but their bets could start to tell you something about that. And you have to know that your opponent doesn't know what cards you hold, but your bets could tell them something about that. And you have to think about all of that to play the game well. There are actually many variants of the game. We're going to talk about limit and no limit, but we'll come back to that. Okay. Before I go on to really talk about how AI can handle games like poker, I want you to harken back. Some of these is going to be easier. Some of this is going to be harder. I want you to harken back to when you took an AI undergraduate course. And you probably, recall you might have actually maybe did a program. Maybe you actually wrote a program to play chess. Some people in the audience probably have written chess playing programs. I actually did a Connect 4 program. But if you're probably more recent, maybe you wrote some AI to play Pac-Man. But no matter how, any of these games, I'm going to remind you of what you learned to do, the technique that you learned to do that is going to be able to be able to handle these games if you write a program to do so. Okay, so the way this works is you are going to make some decision, and the way you're going to think about it is you're going to think of, I have actions that I could take, and then my opponent could maybe take some actions after that, and then I'll be in some new state, and I could take some action after that, my opponent could take some action after that, and I'm going to look through these possibilities until I get to the end of the game, and I'll find out if I won or if I lost. And then I'll look back and say, okay, well, at the end of the game, I'll, of course, take a winning move. And my opponent will try to take a move that causes me to lose. And I can basically start to work my way back to make some decision at the top of that tree. Now, that doesn't work if your game is big. So if we were talking about like the game of chess, that's not what you did. Because you realized the game was too big, and I'm never going to get my way down here. Or even be able to search through the possibilities to get there. So what do? Well, we chop it off. We don't actually consider all that depth. We actually pretend like the game's really short. We're only going to look a few moves ahead, and then we're going to stop. And then what happens when we stop? We're not at the end of the game, right? We've only looked a few moves ahead, and we're at some point, and we're now going to have to figure out what to do with that. And we're not at the end of the game, but we're going to pretend like we kind of are, and we're going to have an evaluation function that's going to tell us how good is it to be in that state. If it was the end of the game, we'd know. We'd be a winner or loss. But if it's not, so we're going to have some heuristic that's going to tell us whether that's good or bad. And then we'll pretend like that's, in fact, the result of getting there. So now we have this small game that we have to reason about because we're going to use evaluation functions to summarize that big future. Does this make sense? Everyone probably remembers this, hopefully. Wow. No one shook their head up and down. That was weird. What did you guys learn in your AI class? We good? This make sense?
Yeah.
Okay. So then when you act, though, what actually happens? You're not actually going to play that whole action to get to some state. You're only going to take one action, and then maybe your opponent will take some action, and then you're going to get to take another action again, and you repeat the whole process. Right? So now I can actually look deeper because I'm now 2 moves further into the game. So now I can repeat this process from this position. And in fact, when I do so, I forget everything that came before. I don't need to remember how I got here anymore. Like the board position summarized it, I'm now at some new state with the pieces in a different place, and I'll start my search from there. And I'll just repeat the same process. I have evaluation functions that are now deeper into the game, closer to the end. I'll figure out what action to take. I'll take it, my opponent will take some action, and then again, I'll forget everything that came before, and I repeat this process until we actually get to the end of the game. All right, that is a fundamental idea of artificial intelligence. Like, that is at the core of so much of AI, right? It's obviously at the core of how we play chess. It's at the core of AlphaGo, even with all the extra bells and whistles added onto it. It's at the core of reinforcement learning, right? Reinforcement learning is about summarizing all of the future with an evaluation function, so we don't have to reason through that when we do our thinking. It's at the core of like robot path planning. It's at the core of laying out circuits on circuit boards, right? It is one of the most fundamental AI and computer science algorithms. And the tricky part is we can't do any of that in the game of poker. So why not? Like, this isn't what any of us ever did, and why not? The first problem comes from, I'm not at a state. Like, well, I am. I'm at a particular state of the game, but that isn't enough to tell me what's going on. There's the other player's cards. So how can I search through? If I took this action, maybe I could think through that. How do I know what my opponent would respond when I don't know what cards my opponent's holding? So I can't really think about it from a particular state that I'm at. I have a second problem in that I can't forget everything that came before the way we did before. Way we do in perfect information games. And that's because what came before is very, very important to tell me what my opponent knows about my cards and what I know about my opponent's cards. I actually need to remember something about the history of how I got here. And lastly, I can't really go and evaluate these states at the end sort of independently, because they too depend on beliefs. If I were to know that I have good cards, I might know that that's probably a good thing. It'd be even better if I knew I had good cards and my opponent had bad cards. That would be even better. It'd be even better if I knew I had good cards, my opponent had bad cards, and my opponent doesn't know I have good cards. That would be even better, right? So the value depends on what everyone actually knows. I can't really just have a value of sort of saying this state. We'll come back to that. Some people who know that word state might be like bristling a little bit. And it's okay, because the fix to all of this is going to make you go, yeah, I knew that. Okay, but anyway, if that does, it's fine if that didn't make any sense. Okay, so what did we do, or what do we do? This isn't what we do. So what do? We actually have to think about the whole game at once. The problem is how you play when you're holding a pair of aces is intimately connected to how you play when you're holding a 2 and a 5. Because your opponent doesn't know which of those two things you have, and so how you play with those situations will determine what your opponent can infer from your actions, and so it matters. You can't just chop the game up and look at isolated situations while you play. So that means we're going to do our reasoning by thinking about the whole game at once. But that's terrifying, because these games, the poker games, are still big, just like the perfect information games are. And so we're not going to quite be able to do that. So what do? We actually only look sort of at like a sparse version of the game. We're going to like rip out whole chunks of it. So we're only going to look at certain paths through the game, and we're going to get rid of other ones. Some of these paths are things like, I'm going to only look at a small set of ways the cards could be dealt out. So it could be, I'm not going to look at all the ways the betting could go. I'm just going to get rid of some of them and assume that no one can do that. Now, that's a slight problem, because so now we're going to do this reasoning, and I'm not going to tell you how we do it, but now we take this much smaller game, we process it, we figure out how to play in every one of these situations, and then when we're actually playing the game, of course, we have a problem. What if one of those things that we said couldn't happen, what if it does? Right? We have a problem. And so what do? We just pretend it's like this other thing over here. Okay, so that works for like bets. If someone makes a bet and we didn't think that was possible, then we'll just pretend like it's some bet that we thought they could have made. For cards, we're a little bit smarter. We actually reason about sets of cards together in order to try to get rid of the complexity. So we'll actually just smush together holding a pair of aces and holding a pair of kings and pretend like they're the same. And so we know that while we're doing the reasoning, but we still have to actually consider much fewer possibilities and how it plays. And so we do all of this before we sit down, even at the poker table. So this is a big, massive reasoning up front. We're going to figure out how to play in every situation that's in our sparse version of this. And then when we sit down to play, we're really just looking things up into this table. Very different than what I just described we do in chess and checkers and Go, where we do most of the reasoning computation on the fly while we're playing. Here we're going to do it all offline before we sit down and play. We're going to store it in a big, massive table. Okay, so before I get to deep stack, which is what this talk is about. I want to tell you a little bit about an older result that's just from a couple years ago that will also sort of help illustrate this difference as well too. So this is work on a program called Cepheus that plays heads-up limit hold'em. So this is the smallest variant of poker that humans actually play. So at the time, this is the way we kind of looked at what we could do. So given that methodology, where I said we're going to solve sort of the whole game up front, how big of a game can we solve up front? And this is sort of showing over the years, going back for over a decade, how big of a game we could solve. So it wasn't until 1993 that we actually had a polynomial time algorithm that could solve games of an imperfect information form. So before that, it was dreadful. We could have games that had like 10 decision points, and that was the end of it. So now, finally, in the 90s, we could do things that have in upwards of 1 million decision points. And then things didn't really change for a decade, and then we started to see some fancy new methods. Counterfactual regret minimization is the basis for a lot of these. I'm not going to go into the details of that, but we started seeing order of magnitude jumps in the sizes of games that we could deal with. And so up until a few years ago, we could do games close to 10 to the 11 in size. So heads-up limit, the smallest variant of poker that humans play, is here. So it's a few orders of magnitude bigger, but not insane. Like, this is within reach. And that was what Cepheus was set out to do, was could we try to get there? Now, this abstraction methodology, which was what everyone was doing to this point, this is smushing things together that we know are different, but pretending that they're not, it actually kind of works in heads-up limit. So it was in 2008, when we could solve games about this size, that we were able to beat poker pros at the game of heads-up limit. So while as we started to solve bigger and bigger games, we were getting better. But at this point, when we did abstraction from a game with about 10 to the 14 down to a game with about 10 to the 8, so we were smushing together about 1 million different situations that should be different. We were pretending they're the same. We were still able to beat poker pros. But the question is, how close are we to being able to solve it when we're this far away? All right, I'm going to need another poker interlude for a minute. In order to evaluate poker programs, you don't have like a win-loss or a percentage of wins and percentage of losses. It matters how much money is actually changing hands, or the stakes that's actually moving back and forth, which is typically measured in blinds, which are the blind bets that are actually being made, which are these millibig blind per game numbers is based on. You don't need to know at all what that abbreviation means, except for I'm just going to give you some numbers. So when you have two programs play against each other, they're going to give a result of how much is one beating the other one by. If one of those programs was the fold on every hand, then it would lose 750 millibig blinds. So you would expect programs and players to be better than that, because there's an obvious strategy that guarantees you don't lose more than 750. A poker professional is hoping to win by about a rate of 50 millibig blinds per game, and that means they can sustain the sort of luck inherent in the game, and they can make a living playing that if they can do that at a high enough stakes level. Of course, if you had a program that was guaranteed that it never lost more than 0, like it never actually lost any amount, then you would have a perfect program. So these things that do exist, we know that Nash equilibria for this game exist, and so there exists a way of playing any form of poker that guarantees it won't lose money no matter who it plays against. There's one more number that I couldn't quite put on here, which is there is a number that if you got this close to being perfect, if you could guarantee you never lost more than 1 millibig blind, then it would actually be not humanly possible in someone's lifetime to determine that you were in fact not perfect. We call this, if you could get down to that level, you've essentially solved the game, even if you didn't get down to 0. Okay, so that was set out as our goal for Cepheus. We wanted to essentially solve heads-up limit. And so I showed that result that said we were still a few orders of magnitude away, but there's a different way of looking at that same result, which is saying, how close to that perfection are we? So now I've told you what this y-axis is. It's this millibig blind number of how close to perfect are you. If you played against your worst case adversary, someone who knew exactly how you played and knew exactly with what distribution you took all the actions you take, how much could they beat you by? And so these are our programs as we made our abstractions bigger. So as they solved bigger versions and we did less smushing of things together that we knew are different but we pretended weren't, we can see that, yes, indeed, we're getting our exploitability to go down. That's great. We're actually doing better as we smush less things together. The problem is, this is how big the whole game is. And this bar down here is what we were trying to get to. This means we've essentially solved it. This direction that we're headed, even if we start doing more and more abstraction, it's unclear that, even when we get to being to where we can just outright solve the game, it's not clear that we're going to outright solve the game. Right? This is a problem. Like, abstraction isn't really getting us closer. Like, it seems to almost be hindering. We like to see this going down at a much steeper slope than this. And so abstraction doesn't seem, for heads up limit, it got us to be able to beat top players. It's not going to get us close to getting an essentially solved solution. So CFS did actually get there. It did it by throwing abstraction out the window. So that's going to be the theme of both of the two programs I'm going to talk about. We don't want to do abstraction. And so there's a lot of complexity in Cepheus of what it did. It had a new game-solving algorithm that solves games faster. It had to deal with how do you store the resulting strategy, because we're not going to do abstraction. We're going to consider all 10 to the 14 decision points as separate and something you need to reason about. That means you need to store a strategy that's 160 terabytes big. That creates problems. So we had to do a bit of work on compression. How do we distribute this across a large number of CPUs? And so on. So we started a compute job 2 years ago that ran on 4,000 CPUs on Compute Canada, with the goal to try to see if we could get our exploitability down to below 1 millibig blind. Just as points of comparison, remember that's the always fold number is 750. Polaris was exploitable. This is the program that beat Prose, was exploitable for a little over 200. The previous and best known exploitability was a little under 100. Notice that all of those are well over 50, the number that we expect Prose to actually win by. So none of the programs up until this point were particularly good in the worst case. And so the computation runs, and in the first 10 hours, which is also 5 CPU years, just as a starting point, we actually got under always fold. So that's good. The program is actually playing against itself, learning to play the game. And so in 10 hours, unfortunately also 5 CPU years. I don't know which one. I like the 10-hour number, but maybe it took 5 CPU years to get there. It figured out how to do better than to always fold. Roughly by the end of the day, or 16 CPU years, we are underneath what it took for Polaris to win. Now, close to a week in, we cross the single best, but we now also have done 59 CPU years. If you notice, the x-axis is a log plot, which means time's about to slow down. This goes for a very long time. This was now 69 days of computation later, or nearly a CPU millennium of time, after which it's played more poker than all of humanity combined has played. We have a perfect, or essentially perfect, heads-up limit hold'em player. So that was really cool. That was the result we had 2 years ago. But today's talk is about DeepStack. So DeepStack plays heads-up no limit. That's the change here, right? So let's go back to Dr. von Neumann. Okay, so final poker interlude. What's the difference between limit and no limit? In limit, the way these bets go, the way you wager who's going to win, is it looks like this. Someone says, I bet. The other person says, I raise. The other person says, I call. There isn't any other actions that you could fold as well too, meaning I don't want to call your bet, I'm going to give up on the hand. But you don't get to decide how much you're betting. That's actually determined by the rules of the game. So all the bets are of a fixed amount. And there's also a limit to the number of bets that can actually be made. In the game of no limit, it doesn't look like that. You actually get to decide how many chips from the chips in front of you you actually want to make a bet. And so someone might I'm going to make a bet of 400. The other person might say, I'm going to raise you 8,192. And that's a different bet than 8,191. And then the other person, of course, this game, if you've seen it, the poker played on television, you've probably seen this form. Of course, someone can also say, okay, I'm going to go all in. I'm going to bet all the rest of the chips in front of me. And so that's another aspect of the game. And that's sort of how the no limit game works. Okay, so how does this change the picture? So just to put this on this context of, we had this graph of saying how did our progress gone at solving games, and we put heads up limit hold'em on this graph, smallest variant of poker that humans play. So let me show you where heads up no limit hold'em is. Okay, there. Sorry, that took a while. Sorry. It's at 10 to the 160. Right? So the number of atoms in the universe is closer to 10 to the 80. So it's like there's an entire universe inside of every one of those atoms, and then you count all those atoms. Anyway, it's a really freaking big number. Yeah, this number is close to the size of Go. So this game is now closer on par, whereas heads up limit might have been on par with checkers. This is closer to be on par with Go. Now, I mentioned that we could, with abstraction, beat human players at heads up limit. And that's going to be the goal of DeepStack. We want to try to beat human players at heads up no limit. We're not going to try to solve it because that's outrageous and we're not going to get there. But we want to try to see if we can beat human players. But now the gap of the largest game we can solve is now enormous, right? Think about what abstraction has to do. We can now solve a game that has 10 to the 14 decision points. That means we're about to put, if we can do abstraction, 10 to the 146 decision points and smush them together, right? We're going to take an entire universe and pretend that it's an atom. Even worse than that. If that doesn't work for you, here's what it actually means. This is how you would play chess, according to the abstraction methodology. You would say, oh, look, chess is a big game. That's too hard to think about. Oh, here's a game. I could think about that. Okay, I'm going to solve this game. I'm going to figure out all the ways to play it like I would solve like a tic-tac-toe game. And then I think, oh, the best move to do in this game is that. So in the original game, I'll do that. That's probably good. That's what our poker programs are doing. Right? They just have no idea what's going on in the game, and that's why they don't win. Okay, so that's not what we want to do, and that's not what our chess programs do. Our chess programs don't have to do this because they don't have to think about the whole game up front. They can reason about this position as it arises in the game. They don't have to think about them all ahead of time because they can search the ones that actually occur within a game. That's what we want to do. This is what DeepStack's going to do. Okay, so let me remind you of the problems I said of why we didn't do this and why we can't do this. So I said the first problem was we're not at a particular state of the game. We're actually at more like something like a distribution of states. We're actually at what are the possible cards I could be holding, what are the possible cards the opponent could be holding. We also can't forget everything that came before that because that's going to tell us information about the cards that players are holding. And we can't evaluate states just independently. We actually have to take into account what do people know about the cards, each other's cards, to be able to evaluate a resulting state. Okay, so DeepStack's going to solve those problems. Excuse me. Okay, so how are we going to do that? So here we are at some point of a game. Some actions have already been taken, and we're at some decision point in this game, and we need to figure out how to act. Now, this decision point, again, as I said, we can't think about this in isolation. We have to think about things that my opponent could know and I could know, what are possible cards my opponent could hold. But if we fix that state as no longer thinking about a particular single position you might be in, but the distribution over what I could know about my cards and what my opponent could know about their cards, if we talk about state in those terms, so now it's more like a collection of things, then now I can start to reason about this game independently of what happens before. Now, I'm going to have to remember some things that came down this path, this white line. I'm going to have to remember some things. But I don't have to actually do this. Well, let's look at what I have to remember. The first thing I have to remember is I'm going to have to remember what possible cards could I be holding? What's the distribution of cards I'm holding? Now, I know I was dealt a particular set of cards, but I need to think about what other sets of cards I would play the same way that I did. And so I can do that as long as I actually think about it all along the way. And so DeepStack is. DeepStack's never really actually looking at its cards. It actually figures out how to play with all the cards, and then peeks at its cards to figure out what action it's going to do, and then kind of forgets it. Because it always is going to always think about every possible pair of cards, every step along the way. So this, in effect, is telling you this is all my opponent could possibly know about my cards. And even for the opponent to know that, they would have to actually know exactly how I'm playing, which they might not. You might think that the other piece you need to know is what is my opponent's distribution of their cards. But that's really tricky, because I don't know how my opponent's playing. It turns out that that's not actually the quantity you want to know anyway, and it's a little bit tricky to try to go into detail of what you actually want to know. But the actual value you want to know is what you actually want to know is what is the value of your opponent holding different cards at this place. Because that's going to decide whether your opponent would want to bring those cards here or whether they would want to deviate and take them somewhere else. And so rather than keeping track of the actual distribution, at every point along the way by having these values, I can recreate the distribution and still guarantee that they wouldn't want to deviate from that distribution and play a different way based on how I now played in here. Because the tricky part is if I change how I play in here, they might not want to take the set of cards I think they're taking in here. They might choose to take some other branch. So to have a game theoretic guarantee, I need to know what they could have gained from playing into here. And so those are the two quantities I'm going to need. They're actually vectors. The one is the probability distribution over all the cards I could hold. And the other one is a vector over all the cards my opponent could hold. What value do they gain by bringing those cards into this place? Okay, so if I have those two quantities, then I get to do my first problem. I can forget everything that happened up until this point. I don't need to remember exactly how the betting goes. All of that gets summarized into my range and my opponent counterfactual values. Okay, so that's great. It means that now I can solve this little decision point. I could take an action, and then I could solve it, resolve it again, and this would be fine, except what happens at the beginning? Because at the beginning of the game, I'm still stuck with one of these impossible problems again. At the beginning of the game, sure, I need a range and counterfactual values, but now I have to solve this big triangle, and big triangles are bad. So, so what am I going to do? Well, we also have another problem to, well, okay, this is going to be fine. Okay, so what am I going to do? I'm going to do the exact same trick that we did with perfect information games. I want to cut off the search. Right, so we said we ran into another problem there, which was how do we evaluate the results of these leaves of this tree? And the way we're going to evaluate them is we have to evaluate them as sets together. We're going to, just like we have sets at the top of the tree, which are possible cards that you could have, that's going to be here true here too. We're going to come down to a state where I could be holding a distribution of cards and my opponent could be holding a distribution of cards. And now, when I actually do values, the values have to be over the beliefs of here's what my opponent believes that I'm holding, and here's what I believe my opponent's holding. And it's going to be the value of every possible hand that you could hold under those beliefs. That's the value that you need to know. And then you can pass that back up. Now, it's a little bit trickier than that. We often think about search as sort of recursing this triangle once, like it sort of walks down, gets a value, propagates it back up. Because this is game theoretic and there's still imperfect information even within this little chunk here, it actually goes and has to re-go over this tree many, many times to revise its probabilities of taking actions to arrive at the game theoretic equilibrium. And so when it gets down to here, initially it's believing that, oh, everyone's playing randomly because I don't know what else to do. When it gets down to this state, it actually has a certain range. It updates its values, change how it's going to play according to these regret minimization algorithms. And now when it comes back to the state, it actually has different beliefs about everybody. So this valuation function actually has to get evaluated many, many times for the same set of states just to resolve one iteration of solving this. Okay, but if we've done that, then now we can take action. My opponent could take some action. And now I'm going to try to, I'm going to now do my search again from that place. I'm going to do my look ahead from that place. Yeah?
Do you have a guarantee that it will converge, or do you stop it if it doesn't converge?
We have a guarantee that it converges. Yes. So we do stop it before it converges because convergence is not a finite time statement. But we can control how much computation we use and when we want to stop it because it's, there's epsilon left.
The strategy for stopping it is just the number of iterations.
Currently, we have a fixed number of iterations, but we also there is a theorem that says how close to epsilon we'd get given that we're doing that fixed number of iterations. But in practice, we do that more based on the amount of time we have to act than we do it because we're getting to a certain epsilon. Okay, so now we have one problem left to solve, and that is we had our range and counterfactual values from the previous state, and now I want to try to forget that previous state and how we got here. So I'm going to need to update these range and counterfactual values. So two things have happened. I acted and my opponent acted. And the first thing that happened is when I act and my opponent acts, it's easy to update them because I actually know my strategy. So I can just apply Bayes' rule to my probabilities of taking actions with each of my cards and now say what's the new distribution of cards I could hold. And so therefore I can update my range easily. I can also update the counterfactual values because that was actually part of this light blue triangle. The way we solve it is we do counterfactual regret minimization. The values are embedded in the solution. And so as long as that dot sat in my game, then I can actually get the counterfactual values of how they change for my opponent. The trickier one is actually the next one. How do I go through my opponent's action? Because my opponent also, when I solve this light blue triangle, even with it being small, I still probably cannot consider all the bets my opponent can make. So what happens if my opponent now makes a bet that's different one of the ones I considered? It turns out that with these counterfactual values, that the only thing they could have done is made a bet that made it worse for them. And so I actually don't need to touch them. The values are a bound on how well they could have done, and that bound is maintained even after they take this action. My range also can't change because my opponent's actions can't cause my distribution to change. So it turns out over the opponent's actions, I don't need to do anything at all. That means I never have to do, for the poker people in the audience, I never have to do translation at all. Okay. All right, fine. All right, so where are we? So that's it. That's the whole idea. So we have this perfect information set up where we are going to take action, do a look-ahead search, figure out what action to take. We'll then only take that action, and then we'll recompute the next action on the next step. The way we make it tractable is we don't look to the end of the game. We only look a few actions deep, and then we'll use an evaluation function. And now what do we have for imperfect information games? We're only going to look a certain look ahead deep. We're going to compute the action we're going to take. We'll take it, and then we'll redo our computation on the fly, where we now need some valuation function that's going to run values on beliefs of states that you would result in. Okay, and we're going to have to remember, unlike the perfect information games, we'll have to remember some things, but we can actually update those efficiently. Now, the really cool thing about this is we've just unified, for the first time, perfect information games and imperfect information games in a way that we've never been able to do before. The other cool thing about this is it means that the 50 years of experience we have with perfect information settings, we can start trying to steal those ideas into imperfect information games. And so we've already stolen one in. There's many more that you can do. But the one we're going to look at is, where does this evaluation function come from? And exciting new result from AlphaGo is, well, maybe we can A, learn it. That's not new. But B, maybe deep learning is a powerful way to do it. And so that's what we're going to do. It's seemingly obligatory to have a pretty neural network picture in a deep learning paper. So here's our pretty neural network picture. This is actually, I'm not even going to go through this because actually the neural network we used is really vanilla. Like, all it is a fully connected series of 7 fully connected layers with ReLU connections between the two. There's nothing really fancy about this. There is one cute trick, which is at the end of trying to compute values, we actually know the values have to be a zero-sum game. So the values for one player has to be the negation for the other on expectation. So there's this cute little trick that after we run through, we're actually going to compute how far they are off in case they differ, subtract it off to force them to be zero-sum. Turns out that's all differentiable, so you can still run the derivative all the way through a network that guarantees that it's zero-sum. Okay, but the catch, though, is what are we going to feed into this? How are we going to train this network? So now what we have to do is we have to feed in poker situations. We have to feed in, here's the board cards, here's what the pot size is, here's what you believe about your opponent's cards, and here's what your opponent believes about your cards. That's what the neural network takes. It actually takes beliefs of what everybody has, of what's going on in the game. And from that, it's going to get values of what everyone believes. So what we did was we actually generated random poker situations, including random beliefs about what people had. And we solved them outright using a game solver that that was using older techniques. And then we'd plug them in so this could summarize what those results were. And so we started with just river situations. It would train to learn how to play on the final round, which is small enough for us to solve. And then once we trained up a network to do that, we could now actually have something learn to play on the round before that, because it would basically solve that game by resorting to its river neural network to play for the round after that. Okay, so we could essentially do an RL-like bootstrapping. It was a little bit by hand, but an RL-like bootstrapping backup to get further up the tree. Okay, let me tell you about evaluating this. Yeah?
Just wondering, there's no bound on the number of rounds here, though. So this bootstrapping, how do you truncate?
There is bounds on the number of rounds, because the rounds were river, turn, flop, and pre-flop. There's only 4 rounds in it. But so we're not going to do look ahead based on the number of bets. We're going to do look ahead based on a whole round. So it's a little bit weird because there are paths of through a round that are very long. But there's a couple things you can do with that. One is that we're actually going to still do this idea that after a few actions we can actually say you're not allowed to make certain bets anymore. And that can force it so you can't make little tiny bets, which is going to prolong the round. And so that could because we're never playing according to that, it's not so bad. We're only using that to do value estimates. It's much like, hey, doing random rollouts from go positions isn't a bad idea for getting a value of a go position, but you would never want to play as if the opponent's doing a random rollout. And that's kind of the trade-off that DeepStacks do. Any other questions? Okay, it turns out that evaluation in poker is nearly as hard as the poker problem itself. I think a quarter of the Computer Poker Research Group's papers are actually about how do you evaluate programs. And it's hard for a couple of reasons. One is the imperfect information nature. It means that how you exploit programs is different. I'll talk about that in a second. Another one is because there's so much luck in the game that you often just have to play an inordinate number of hands to actually figure out who is better. So the DeepStack paper actually makes two big contributions to the evaluation part. The one I won't go entirely into, but I want to show you some results for. Ideally, if you wanted to measure how perfect, like when we did the Cepheus result, we were trying to get a perfect poker playing program. We wanted to get something that essentially solved the game. And DeepStack's trying to do that too. It's trying to approximate a perfect player. But it's not going to necessarily get there, so you could measure what's the gap. Like if something knew exactly how DeepStack played and studied it, and it was its worst case adversary and played against it, how much could it beat it by? And so you might want to do that. But the problem is that requires traversing this 10 to the 160 tree, so we're kind of out. Like we can't exactly compute a best response to DeepStack. But we can actually try to estimate it by doing like a greedy best response. We'll just greedily take actions to try to see if we can exploit it over like one ply search. And that's what local best response is. I'm not going to say any more about what it does, but it does get to look at the ranges that DeepStack holds. So it gets to know information that no human could know and sees if it can exploit it. So we did this because we wanted to benchmark other programs. So all these other programs that had existed up until DeepStack were all these abstraction-based programs. So how do they fare when someone tries to greedily exploit them? And so these are the results of running against these two programs were second and third in the annual computer poker competition from a year ago. So these are strong players, strong computer players at Heads Up No Limit. Remember, I haven't changed the units here. This is the same units as before. 750 is how much you lose when you always fold, and obviously a greedy strategy isn't going to get any more than 750 out always fold. These are what the other three programs are. They're disasters. They lose by many of them by 4 times as much as if they just folded every hand. They fundamentally do not understand at all what's going on in the game, and you can actually beat these programs without even making a bet. So if we actually take the betting action away from the local search, the little local best response, it's not allowed to bet. It can only call, and it can only fold. So these things are just making fundamentally bad bets. They're making fundamentally bad folds. They're making fundamentally bad everything. And you still can beat them for over 3 or 4 times always fold. Now, they also have to do abstraction on the cards. So probably you might think where this is coming from is they don't know what cards they're holding. And so you're just finding these situations where like you have better cards, and then you're going to take them for all their chips. That's probably true. It's probably a big hole in their play. But we can also do something else. We took a program that now has perfect card information. It's playing a slightly smaller game. There's smaller stack sizes, but we gave it less betting options in the abstraction. So this now has to do lots and lots of betting abstraction, has to confuse the bets. It doesn't know those, but it knows exactly what its cards are, and it still gets beat for 3 times more than always fold does. Okay, so abstraction, you fundamentally have to choose between whether you would like to be that one or that one, and you get to trade off between those 2 things. And you're just choosing between this disaster or that one. DeepStack, where does that sit? Best response, local best response can't find any hole in its play at all. It actually loses to DeepStack. So it either means that DeepStack is much less exploitable than these other programs, or you're just going to have a much more complicated and sophisticated search procedure to find its flaw.
Can I ask a question?
Yeah.
So human pro players obviously are grouped near some ceiling of performance on this metric, and you're trying to beat human pro players, but is that ceiling pretty crowded with people, or is there like specific individuals that are like...
I don't know it would be very hard to put pro players or any players on this graph, because to be able to run something like this against them, they'd have to be able to tell me the range of cards that they hold. They'd have to tell me how they would play with every set of cards. Right. But I would also suspect that humans would also perform quite poorly on this metric. I think if you could somehow get their play to be static enough that you could actually measure it this way, I suspect that they're mainly playing well because that they don't reveal that information. This is why poker players are very, very careful that they don't want things like their hand histories for other people to see them. Because if you could actually see what cards they hold all the time, then you'd be able to start to decipher things that local best response gets, like what's your range in particular situations. So this is why they're so guarded, I think, about their hand histories and releasing them. But we also want to play against pro players. Like that's the other way that you could try to analyze how far we've come with DeepStack. And that's tricky because of the amount of luck that's in the game. So if you were to try to separate an amateur and a pro player, now remember I said that a pro player is trying to win by about 50 millibig blinds. So suppose you had someone who was ahead of someone else by 50 millibig blinds. How long would they have to play before that would become statistically significant and you would know? Turns out that number is about 100,000 hands. So that's a long time. That'd be like a month of the human pro just playing and maybe eating, maybe sleeping some of the time. It's hard to get someone to do that, especially if someone makes a living playing it, because then you either have to pay them for their lost winnings or anyway, it's just hard to do. So could we do better than that? And so we've done a lot of work at what I'll call variance reduction, which is the idea of looking at how a game played out and not just taking the money that changed hands, but actually looking at the decisions that were made and seeing if we can actually get a better estimate of who the better player is. And I'm going to try to do this. Okay, so I think our new technique for variance reduction is super cool. And so I'm going to try to explain it to you in 5 minutes. Okay, here we go. Here's a hand of poker. This is all from the human's point of view. So we want to analyze how well the human played. The human was dealt a pair of cards, and then the bold numbers, the bold actions here are the bot's actions. So then the human, say, raised 200, and the bot called. And then in Texas Hold'em, the way this works is 3 cards are revealed that everyone can see. There was some more betting, and then another card was revealed. There was some more betting. Another card was revealed. There was some more betting. And then finally, now we get to the river, and everyone there's no more betting left to be had. And so then Deep Stack shows its cards. Okay, so this is just one view of a hand from the human's perspective. And so one of the things we can do is we can say, okay, well, given this happened, I know how much money actually changed hands. Right, like I see the whole game now, and I know, that I actually don't even know who won this hand. I guess the ace-4 won. Okay, so I know that Deep Stack won this particular hand by. Oh, did I get it wrong? There's a flush. Okay, say.
That's why it's such a sad hand.
It's a sad hand. Okay, I made this like a month ago, so I haven't looked at this hand in a while. Okay, sorry. So the human actually won this hand. So we know the dollar number here of what actually transpired, and that's all that would happen. If you were trying to do regular evaluation, you would just say, yep. Human won the hand, go to the next one. And you would just average those numbers up. And there'd be tons of variance. Okay, so what can we do? Well, the first thing to observe is that we actually know Deep Stack's ranges. Right? We know with what cards it holds at any given moment. Right off the bat, we know, for example, it's holding any 2 cards that aren't the Queen of Clubs and the 5 of Clubs. We know that for certain. It was random 2 cards. They're all equally likely. But we also know it everywhere else. After Deep Stack made a call action, we can actually say, well, with what pairs of cards would you make the call action? With what probability? Use Bayes' rule, and we get a new distribution on what cards it could hold. And we can keep doing that all the way through. And when we get to the end, right here, we actually know exactly what are all the pairs of cards you could possibly hold at that moment in the game. Okay, that's going to become useful. Second thing that becomes useful is we're going to need something that's going to give us an estimate of something. I'm going to call it V. That's important, a distinction. It's going to try to, what I want to do is at every moment in the game, I want to try to have something that's going to give me an estimate of, without looking into the future, just with that knowledge there, up until that point, what's the value? How much money do you think the human is going to actually win? Okay, so right off the bat, you might say, okay, well, I know Deep Stack has uniform random over all pairs of cards, but I know you got dealt a Queen 5 suited. So that's, I don't know, it's kind of medium. So maybe I'd say, yeah, you'll break even, like on the hand. So I'll come up with some value. But now after I see the raise and then Deep Stack called, Deep Stack called the hand, that's probably not so good for me. So now the value might go down. Okay, so I'm going to do this at every step. I'm going to compute the value, and I get to see the range of Deep Stack, and I get to see that everything came before. Okay, so that's the values that I can have. Let me look at one really obvious thing that I could do. The value right before Deep Stack reveals its cards, that value is trivially computable. Like, I don't need any fancy estimator here. This value is just roll out all the cards Deep Stack could hold and look at whether Deep Stack would win with those cards or lose with those cards. That's what that value should be, right? So that's what that value is going to be, and that means the difference between this and this number is on average 0, right? Because this number on expectation is that. So that difference on average is 0. Yet that difference will be highly correlated with who's actually going to win the hand or not. Right? If Deep Stack happened to be on the high end of its range, it's more likely to win the hand. If it's on the low end of its range, it's less likely to win the hand. So I can actually take that number and just subtract it off from the winnings. It has expectation 0. I haven't changed the actual expectation of the estimator at all. but I've subtracted off something that's correlated, so I've reduced the variance. All right. I hope that makes sense, but we can do way more than that. We can do a whole lot more than that. This value right here, I can do the exact same trick. I'm never going to actually compute a value here. That one is all that's changed is new cards were revealed. The cards come randomly dealt from the deck. I know their distribution. So I can guarantee that that value is just that value in expectation. And once I've done that, that delta is now on expectation 0, but yet highly correlated. As long as my values are good, they're going to say, yeah, if those cards helped you, then that's bad for me. And so I should subtract that off because that wasn't anything you did. That's what the cards did. So I get a chance correction every time chance takes an action. I can go even further. When DeepStack takes an action, the value change here, I know its probabilities that it takes all of its actions. It's fixed now. So it's exactly like a chance action again. If DeepStack gets unlucky and makes an untimed bet, like this was a bad time for it to bluff, I actually know that. If it doesn't do it very often, I can actually make the correction as well here. Because I actually know the probabilities that it would go through. And so in fact, I have every single delta here except for when the other player acts. And I'm subtracting off all the changes from all those things. Now there's one catch. Where does this v function come from? The beautiful thing is that it's DeepStack's computation. That's DeepStack's number. That's exactly what it's doing. It comes straight from the neural networks. And so as good as DeepStack plays will be as good as those v's are. But we're always guaranteed that it is unbiased. It will always produce the same value. If it's a better evaluation, it will just have lower variance. That's all we're going for. If it's a perfect evaluation, it would have variance 0. In one hand, we would know what was going on. Okay, we don't quite have one hand we know what's going on. Turns out, 90,000 hands, we can get the same statistical computation in 3,000 hands of AI value. So that's how good it is. Which we've never seen that before. Like at best, we were able to get 10 and 20% variance reduction in this game. Okay, so doing that, we can finally actually try to evaluate this against good players. So last November, we recruited 33 poker pros to play. We asked them each to play 3,000 hands. We gave them 4 weeks to do it. To give you an idea of one of the players that joined in this recruiting process, it was Phil Locke. He has $3.5 million of live winnings. He's won a World Series of Poker bracelet. So he's in the pool that was playing against it. This is the results. It's a little bit complicated to see. Every one of these dots is one of the poker players. The y-axis here is their performance against DeepStack from DeepStack's perspective. So higher on that chart means that DeepStack was in fact winning. The red line is the 0 line. No one was beating DeepStack by the AI VAT analysis except for 2 people who played fewer than 300 hands. The confidence intervals are showing that that clearly isn't significant. Not everyone finished the 3,000 hands. Only 11 players actually played all the way through. I think some people who, like this guy who you can't see the dot of, maybe got discouraged. The 50 line is here as well, so we were actually beating them again by the win rate that you would want pros to win by. There wasn't anyone that we weren't beating by that who played over 300 hands. The actual win rate was 486 across all of the players. It was 394 against everybody who finished. And just to let you know where Phil Locke sat, he was only in the middle of the road of the people who finished. All right, so I'm running out of time. Let me just wrap up with a few little details. This whole thing runs on a single GPU. So that look-ahead search, we went from, when I told you about Cepheus, 900 CPU years of computation before we sat down to play. Right now, we're running on a GPU because we don't have to look ahead very far. Right? We only ever look one round ahead, and then we can resort to our neural networks to give us value estimation. And all of that, we can all still do it with thinking time being, on average, about 3 seconds in action. We finish a whole hand of our thinking time in about 7 seconds. The laptop's actually over here. If you want to stop by, you can actually play against DeepStack right after the talk is over. One more thing I want to point out about DeepStack is that because it's doing this look-ahead search, it's very flexible, which means you can actually change the rules on it, and the search will allow you to search through with the new rules. Now, the valuation function, which we had to train before we sat down to play, that might be off now, because it might actually, it got trained with in a different circumstance than it actually played. But if it doesn't change too much, you might expect this to do well. So as a result, we can actually have DeepStack play any stack size, which is not something you could ever do with the abstraction-based methods, because you have to resolve everything when the stack size changed. Now it just means that when it bottoms out, it thinks it's in a 200 big blind game, and it's not. So it might get a few errors wrong, but it actually can still play quite well. In fact, because of that, we can do freeze-out tournaments, which is in fact how most human heads-up poker, heads-up no-limit poker is played, where the idea is that if I took half your chips on the first hand, we don't reset the stacks. You now play with half as many chips, and you just have to live with that. And so this is how most human heads-up play is actually done, and you play until someone's out of chips. And so DeepStack can play in that form, which was unreasonable to figure out how we'd get abstraction-based methods to get there. In fact, playing with that idea, we are actually going to start in a few weeks. We're going to start weekly live matches of DeepStack playing against a variety of people in this freeze-out format. We're going to do best of 7 freeze-out tournaments against it. First match is going to be March 29th at 3 p.m. It's going to be streamed on Twitch.
For real money?
We're not allowed to gamble with research money. But actually, there might be side bets going on that we're not privy to or with. Andrew and Nate have a bet for charity between themselves about who's going to do better against DeepStack. So there will be definitely incentives for the players to play. Yeah, if you want to keep up on when the matches are happening, you can follow us on Twitter at DeepStackAI, or you can check out the website. I don't know if this is going to work. I'm going to try something. We had a Poker Pro playing. No, not on anymore. All right. There was a pro who was testing out our system. I was going to see if I could actually watch. Here, this is anyway. They're not. They quit the hand. DeepStack was up by 25,000 to 13,000. So maybe they just. All right. Anyway, I was going to see if we could actually watch someone go live, but they're not playing right now. Okay. So barring that, I just want to again. Oops. You don't see anything. Play slideshow. Okay, I just want to say that I have worked with an awesome team, and they're the best, and some of them are here, and so I'm thankful that I get to actually work with them. I'm also very thankful to Amy, who's given a ton of support, and Compute Canada, who provided lots of computing resources, and IBM, who gave a faculty grant to support this. So thank you very much for your time. Russ.
Heads up, one-on-one. If you're playing against more than one other player, how do things change?
There's 2 answers to that question. The first answer is the theoretical answer. So this whole setup here is very well theoretically grounded. Like there's as Osmar asked, like, can you say something about the iterations? Yep, it all converges. If the evaluation function has epsilon error, we can prove that we get epsilon error in the resulting solution. So that if you can train these things to low error, then everything's going to go very well. And so what does that mean? It also means that every one of these programs are all minimizing exploitability up until these error terms. If you go to multiplayer, first of all, the notion of exploitability becomes unclear. Like, is it if everyone gangs up on me? And how are they ganging up on me? Are they allowed to look at their cards? Are they not allowed to look at their cards? Or are they just out playing for themselves? Then what does exploitability mean? So for one problem, we don't have a nice measure of of how close you are to a perfect solution, because we don't even know what a perfect solution is anymore. There is a Nash equilibrium still. That exists. But the Nash equilibrium doesn't have the same properties anymore, and all kinds of weird things can happen. That I could be playing part of a Nash equilibrium, you could be playing part of a Nash equilibrium, and you could be playing part of a Nash equilibrium, and together we're not a Nash equilibrium. And that can't happen in a 2-player game. Okay, so that's a theoretical question, and I suspect that we're going to have a very hard time trying to figure out how to gain traction for that question. But with that said, we have ran these methods, the counterfactual regret methods, on multiplayer games. And not only are they the best methods we have going, so they win computer poker competitions when there's more than 2 players, but there has been evidence that they actually look like good strategies to poker players. So I actually suspect that whatever CFR is doing, that is actually producing a sensible poker strategy. And yes, you might not be able to say anything about its exploitability. And yes, the players could gang up on it and take advantage of it. But that isn't. But that requires them to be better than they are, smarter than they are. And so I actually think that if you took this technique, there are some issues. You have to deal with the neural networks with multiplayers. The search problem is going to be a little bit trickier. You might have to think about it. But I think with DeepStack, I think we're 1 to 2 years away from even taking down all the multiplayer games.
Are you working on that now?
I haven't decided yet whether that's a future direction to go. We're thinking about it. Yeah.
I have a simple question, technical question. There is an obvious answer, but I wonder if you have
Whether I'll come up with it? It's a test.
Better reasoning behind it. So when you do your evaluation, rather than doing it on one leaf node, you take a group of them. If you have a smaller group, then it's not tractable. If you have too big a group, then you're squishing too much to search space. How do you find the trade-off?
The right group is actually known. The right group is, in fact, the information. It comes from the structure of the game. The right group size is, in fact, what is the information that. One way to put it, it would be if you're a public observer of the game, and you don't know any side's private information, you only know what they jointly know, then you would want to break it up into what they know. All the situations that they can't distinguish, that's what goes in the set. So basically for poker, it comes down to, I don't know there are two cards, that's what I'm going to group into that.
It's always the same.
And it's always the same. Because it's exactly what you need to specify beliefs over. So once I know that bit, like we all know the cards on the table, so I don't need to worry about that. We all know how much money's in the pot. I don't need to worry about that. I need to worry about what do you believe about my private information and what do I believe about your private information. Yeah.
Is there variance in the action time that it takes to make a move?
There is, but it's some of it's just stupid internet variance. Like,
is that
but
variance related
but
to
it's not
the variance of the expected value?
right. So it's two things. There's just straight up variance because of the internet connection and GPUs, and that is going to be utterly unconnected to what state you're in and how it affects anything. The other reason it differs is only by round. So as you get close to the end of the game, it acts very fast. So on the river, it acts very fast. On the pre-flop, we have to do this special caching, actually, which also makes it act fast. And on the flop and turn is where it's the slowest. And it gets upwards of 4 or 5 seconds.
But taken advantage of. And then the flip side of that, is there any human information that it doesn't have, like the time it takes a human to make a move, or
right.
the heart rate, or anything?
So that's right. So we have chosen specifically not to look at timing information of the opponent. One of the reasons we want to do that is because when we play against humans, it means that they can actually talk out loud of what's going on. Which makes it much more entertaining to what's actually happening. Because one of the things we want to do with the Twitch streams is not necessarily to set it up where we're trying to beat them. Particularly, we're only going to play a best of 7, and I bet you our win rate is like 55%. Like you're not going to be able.
What it's like for them.
We want them to be able to talk through what they're thinking and what's going on, and that's where a lot of the reason this is compelling is because you never get to see that any other time, right? If you're seeing live players play, they have to do the poker face thing, right? They can't talk through what's going on in their head.
Thanks.
Any other questions? Yeah.
Just curious, have you seen the deep stack bluff?
Yeah, absolutely. It actually comes entirely out of the game theoretic reasoning. So if I could also let me actually tell you how it arrives at bluffing. Maybe so it's doing this counterfactual regret minimization problem. So this is what it does. It starts off by playing randomly, and it says, oh, if I play randomly, you know what? If I would have actually bet when I had good cards, I'd have made more money, right? Because the other guy folds randomly because I'm playing against myself. So when I bet when I have good cards, well, he's going to fold. And if he doesn't fold, I'm going to win because I have good cards. So it starts to learn that I should bet when I have good cards. And maybe I shouldn't bet when I don't have good cards because when he does call, then I'm going to lose. And then it's playing against itself. So its other side, like it's a little schizophrenic. When it thinks it's on the other side of the table, then it's going to be, oh, should I call this bet? Oh, he's only betting when he has good cards. I'm not going to call it when I have weak cards. So it starts folding to a lot of it's not except for the best hands. So now popping back in first brain says, hang on a minute. If I actually bet when I have bad cards, he'll fold because he doesn't know what cards I have. So it starts betting with bad cards. And then the other side goes, hang on a minute, I can't do this. I can't fold with all of them. I got to call some of the times with my mediocre cards. And so it keeps doing this back and forth, and it's actually getting the probabilities just right. So it actually comes up with a mathematical answer for exactly with what probability and with which cards it should bluff by playing against itself. Yeah.
Have you had any kind of pushback from human pro areas of, hey, we don't want computers solving this because this is a livelihood?
There's the reaction from the poker players is all over the place. There's poker players who are science geeks and think this is amazing just purely on the same reason that other science people would think it's amazing. Like, this is great for AI, this is awesome, and they just don't care about what effect it has on what they're doing right now. There's some people who think, oh, this is awesome because I'm going to learn a ton and figure out how to play the game of poker better because I can learn from these things. And then there's people who, are really ticked because people are going to believe these things are online, whether they're online or not, and that's going to drive people away, and that's going to take all the fish away, and then they're not going to be able to make money. So there's definitely people all over the place. And then there's the people who think that these things are crappy and they can beat them. There's various degrees of wrong in the... Yeah, in the back.
Can DeepStack be used in tournament play? Like, I know you use independent chip model in order to track winnings and stuff.
So as a heads-up freeze-out, you can kind of view that as a heads-up sit and go if you're a poker player, or essentially it's like the two-player version of a tournament, which doesn't sound much like a tournament. But in that regard, it is actually the independent chip model actually makes a whole lot more sense in a two-player game. Like, it's very, very close to being the right answer. And that's in fact how DeepStack's able to play it, is because of the independent chip model. If you went to multiplayer, that would be my first reaction to how to deal with a tournament-like setting for multiplayer, would be to just immediately jump on the independent chip model. I think you could do better. Like, once you actually have something that can play, you could actually solve situations and actually build like a neural network that's going to learn something better than the independent chip model, using DeepStack's own play to figure out what happens when it plays from certain stack situations. So I think step one would be you would just do that, and then you'd have a player using that model to play, and then you could build a better model, and then you could feed it back in, and it's this bootstrapping process again, just like backing up from the river is. You would just bootstrap your way up to a better model of how stacks relate to winnings. All right, I'll take one more question because we're way over time. Yeah?
So there's a certain amount of computation that happens online, and from the numbers it happens like quite quickly, but you have to train the neural networks offline. So how long did that take?
So the neural network training is super fast. It's like a day or two on a GPU. There's preparing the training examples. That's not necessarily fast. And so for the river examples, we took 10 million training examples. So this is 10 million poker situations that were then solved using a traditional technique. And that we used regular CPUs for, and we used about 150 CPU years of computation. So still far less than what actually Cepheus did. And then when we did the river or the turn networks, we now actually need neural networks. So we had GPUs now in that process with the CPUs, and that added another 2-3 GPU years, something like that. So overall, like 150 CPU years and 2 to 3 GPU years of training, which is still on given this, like the other programs that we were benchmarking against, those probably use considerably more compute power than we did. All right, thank you very much.